This is a video of the pyramids in Egypt, and now it is 3D. This is a video of Gastown in Vancouver, and we also made it in 3D. This is Castle de Verdera in Catalonia, and guess what? It's now in 3D.
But how on earth did we create each of these 3D scenes in less than 1 hour?
There is absolutely no way we could have modeled these environments to this level of photorealism.
Let me introduce you, my friends, to 3D Gaussian Splatting, or in short, G-Splats, which is the latest method to create an entire complex 3D scene using only a video.
It falls under the category of radiance fields, much like NURBS, but it's actually quite different.
Here's the thing. G-Splats are faster to train and you can achieve unprecedented level of detail. So let's go and find out how it all works.
First, we begin with a set of input photos that are taken at different angles from a subject. Now, these input photos can also be extracted from a video as an image sequence.
Next, using a mathematical method called structure from motion, the differences between these images are calculated to form the 3D point cloud. Think of it as many dots in 3D space, with each dot representing a point from your photos.
Now, instead of trying to create a detailed model with polygons, each point is turned into what we call a Gaussian. A Gaussian on a graph takes a shape like this. So if you were to imagine it in 2D space, it would be like a Photoshop paintbrush that has a dense center which fades out towards the edges. Now imagine in 3D space, these Gaussians take the shape of ellipsoid. What's amazing about this is that these Gaussians can take various parameters such as transparency values, different sizes, and even color. At this point, the Gaussians enter an iterative optimization process, which is key to its quality and performance. These Gaussians get fine-tuned constantly to match the original photos that we took by adjusting their 3D positions, color, opacity, and how their details vary from different directions.
The training also uses an adaptive density control, which means when a Gaussian is too transparent, it gets removed. Or when a Gaussian is too big for a detailed part of the scene, it splits into two.
To view these Gaussians, we use a technique called rasterization, which projects them onto a 2D surface. We consider their distance from the viewer for depth, and then for each pixel, we'll calculate how much each Gaussian contributes.
Here are some samples of three-dimensional environments that I have managed to create using this new Gaussian splatting technique. It's a very hot topic right now in the field of computer graphics. The principles of what this technology means in practice and what it can really be used for. 3D Gaussian splatting is not a well-defined term, but it generally relates to computer graphics and 3D graphics rendering. Its starting point is in a photogrammetry method that uses digital photograph of real objects or environments as a source. Objects are scanned with a camera by taking as clear pictures as possible from all different angles. The differences between these images are then calculated by computer vision so that the three-dimensional point cloud is formed. All 3D scanning and making of a 3D model with capturing method is based on these 3D point clouds. The typical route to make a 3D model from here is to create surface structure by generating a geometry between these points. Connecting the points together with edge lines forms a polygons, and this polygon structure can then be covered with textures that are captured from those original images where the point cloud was also generated. This is how we make 3D surface models, and they can be used in Blender, Maya, Cinema 4D or all 3D programs that are available today. But 3D Gaussian splatting is not a surface model. It is not made from polygons, and it doesn't have any kind of a texture in this sense. To understand this, we need to go back to the 3D point cloud phase and see how else we can create 3D shapes from these points. We need to think these points as a volumetric model, And here we inevitably came across the concept of nerve. Neural radiance field is a function that describes the radiance properties at each point in the volume. The model trains this field using a neural network and can then render 3D views or perspectives from different angles and positions. But this deep learning method can be very heavy, and training each point from the volume with the neural network is slow. And to facilitate this, the Gaussian splatting method has now been developed. Gaussian splatting does not utilize deep learning methods. It is a traditional and computational technique that employs mathematical formulas and kernel functions for visualizing point clouds in 3D space. One way to do this is by projecting points onto the screen plane and using a spots and ellipse-shaped splats to smooth the projected dots into pixels. This optimized rasterization method creates a smoother and visually appealing view compared to simply rendering the point cloud. It is much faster, and it starts to look very similar to the original image from which it was created. So what can these 3D renderings be used for then? Can I make a Gaussian splatting model and 3D print it? Well, no. Gaussian splatting is not a 3D printable model. You will need to take it back to the point cloud level and start to generate a surface model out of it, as shown before. And in the process it will lose all these transparent and reflective qualities that it can be shown in the visualization mode. So, we need to understand that Gaussian splatting is made for computer screens. It works very well on all kind of monitors, like in virtual reality headset. And VR will certainly be the area of use where this technology will make a big revolutions. And I'm absolutely sure that this will also be a big deal in virtual production, where real-time 3D graphics are run on large LED screens and which are currently used a lot in studio productions of films and TV series. One of these interesting services in the web is Volinga, which already offers the use of nerve-based models in Unreal Game Engine and therefore in virtual production. It's only a matter of time when Volinga also implements these Gaussian splatting models in their services. Japanese developer Genji Asaba has published promising videos on social media where Gaussian splatting is already running in the Unreal Game Engine. And at the same time that I myself have been generating these static environments, the British studio Infinity Realities has developed enormously interesting things around the Gaussian splatting technique. So this technology is now moving at a fast pace, and it feels like it's taking huge leaps every day. It will be very interesting to see what kind of an application will be released in the upcoming months.
5 reasons why you should care, and then let's get into what's actually happening under the hood, because this is really, really cool tech. Number one, this is way faster than nerfs. For comparison, a neural radiance field for this exact scene would take around 10 seconds per frame. Instead, I am zipping around with FPV controls at 100 frames per second without breaking a sweat, though I do crash a few times towards the end there. Number two, this is old meets new. Gaussian splatting is super cool in that it fuses classical computer graphics and modern deep learning techniques. So like nerfs, this is still a radiance field, just without that slower neural rendering part. Which brings me to number three. Unlike nerfs, you have an explicit representation here. So you represent the 3D scene as a collection of these ellipsoidal splats called Gaussians. The beauty of this technique is you can do rendering in real time with a couple of basic computer graphics operations. And unlike photogrammetry, which is super fast to render, you still get all those photorealistic effects because Gaussian splatting uses spherical harmonics to represent all the view-dependent effects and lighting. So surfaces change color when you view them from different angles, giving you all those photorealistic effects, the glint, the veneer, the specularities, without needing a neural network. And while it doesn't use a neural network, the training loop is very similar to deep learning. Finally, number 5, and perhaps the most exciting, Gaussian splatting enables direct editing. So it's not just speed. With Gaussian splatting, you get 3D editing support, so you can select, move, delete stuff, even relight stuff. This type of editing has been so much more tedious to do with NeRFs because they've got this implicit black box representation. And oh my god, NeRFs are just like 2 years old. Here's the new talk of the town. So you've got speed, you've got editability. So it's this like weird middle ground between NeRFs and classical photogrammetry, and super, super exciting for creators. Now, if you want a visual comparison to NeRFs, here's the same data set, about 334 photos captured with a Sony a7S camera, processed with Luma AI and Instant NGP. Honestly, Gaussian splatting looks the best to me, and the fact that it is real time, it just makes it a no-brainer. And to think that NeRFs are only 2 years old, it is wild how quickly things move. So here's the process in a bit more detail. You capture the input imagery, photograph the real scene from multiple viewpoints, basically like you would for photogrammetry. Then you reconstruct the cameras with structure from motion, essentially finding common structure across all the images to figure out the relative 3D position of where the photos were taken. But by virtue of doing this, you also end up with this sparse 3D point cloud. So then you take that sparse point cloud and create a 3D Gaussian splat centered at each of the points in this SFM point cloud. Finally, the optimization process begins. You start rendering Gaussians from the input camera views and comparing the virtual view to the original view. And then you use gradients to optimize the parameters of the Gaussians, right? The position, the size, the orientation to match the photos over time. And since you can't have an even distribution of Gaussians to model the complexity of reality, you have adaptive density control. Essentially adding, removing, and splitting Gaussians during this optimization process to increase the detail where it's needed, for example, the trees, and remove the detail where it's not, for example, the sky. Then you start representing color with spherical harmonics, modeling all these view-dependent lighting effects, optimizing the base color at first, and slowly adding higher frequency bands over time. And look, if you want to spare even more overhead, you can actually turn off these spherical harmonics and you lose some of the view-dependent effects, but oh my god, it still models reality way, way better than photogrammetry. You don't end up with these like wonky looking broccoli trees. You can actually see the lush detail of this tree come to life, and that still blows my mind. Rendering is the coolest part. You can just optimize the 3D's Gaussians into an image plane in alpha blend. So instead of rasterizing a bunch of triangles as you might classically, you're just rasterizing a bunch of these Gaussians. You project these optimized 3D Gaussians onto an image plane and alpha blend them together. And modern GPUs can just rip through these computer graphics operations, which is why you get this amazing 100 frames per second versus 10 seconds per frame. Oh my god. All right, so with all these steps completed, you get photorealistic novel view synthesis that can be rendered interactively at insane frames per second. So compared to NeRFs, this sort of unstructured Gaussian representation gives us simplicity, speed, and quality. So the ubiquity, the ability to distribute these assets and render them on modern computing systems is absolutely wild. I don't need to burn GPU time just to render out a fly-through or deal with some of these awkward hybrid representations where you kind of have a mesh, but there's a neural network working under the hood, the view dependent effects. You don't need to worry about all of that. So it's kind of cool. You got this like OG like physics concept, the spherical harmonics, providing the view dependent effects for realism. Meanwhile, you're using gradient based optimization of the Gaussian parameters to fit them to match the real world appearance. A nice combination of computer graphics and ML techniques. Call it the best of both worlds. So suddenly you don't have these heavyweight meshes. You can render them on device on mobile. You can render them in a browser. You can render them obviously inside a game engine. And so you've got all these possibilities for interactive editing and previewing that you just couldn't do with NeRFs. Like, I cannot overemphasize the benefit of having this editable, discrete scene representation rather than having this sort of implicit black box representation with NeRFs. So this paper is crazy because basically if you like train it for, let's just say 7,000 iterations, it's still better than Instant NGP. And if you go to 30,000, it rivals MIP-NeRF and all the other higher quality approaches for neural radiance fields. Now, there are limitations which we'll get to in the future where certain types of complex lighting and transparency scenarios are still a little bit difficult. This is why it's such a promising technique that could transform 3D capture and creation forever. That's it for this video.